All right, let's get going. Again, my name is Marcus with MLC CAD Systems, and today we're going to talk about tolerances with 3D printing, specifically really tight tolerances, and understanding how accurate and strong we can make the very first part off the line be. So let's talk a little bit about what I mean by the very first part, because a lot of times with 3D printing, it's a very forgiving process, because if you mess one up, you just print another one, right? You learn, you print, you learn, you print. It's great for failing fast, which is why it's so useful in R&D. But we want something that's going to be precise and reliable to create very strong parts where we just have to basically hit print, and we know we're going to get a good part the first time every time. And so I'm going to measure my success in this example using time to first part. I'm just making it up, but time to first part. And the first part is not just the first shape I make. I mean the first part that's actually strong enough. The first part that actually fits perfectly without having to go in and tweak the numbers and the size. The first one to print without realizing I set up something wrong on my supports, or even worse yet, my machine gave me something, we failed, lost a lot of material, or, basically printed and then ran out of material halfway through and the machine didn't realize it. And these problems plague most 3D printing technologies. All of these do. But what you find is that industrial 3D printing, which is kind of this subcategory of overall additive manufacturing, is used in very specific profit centers, right? Ways that your company is making profit, and they sort of supercharge those activities. And in industrial settings, we don't have time and patience and money to sit around and wait. And so we need the first part to be good. That's in prototyping, right? I need an accurate representation of the design I'm going to make quickly, with no delay, so I can quickly fail fast, right? R&D needs to be able to learn and adapt quickly. When it's production, we're talking about jigs and fixtures, right? They need to be strong so they can survive production, but a lot of times they're low volume, so you definitely don't want to build them using traditional manufacturing. But in some cases, you're building things like go, no-go gauges, where the accuracy of that part literally determines the success or failure of all production parts. So accuracy is critical there. And then we talk about low volume production, where repeatability, reliability, consistency is important, because these are parts where we know the part will function as an additive part, but we don't have the quantities to justify tooling and increasing the production and doing something else. So we're going to use the relatively high cost of each individual part, but you take advantage of the zero tooling effectively, and we're just going to print what we need when we need it. These are the applications of industrial 3D printing, and there's three kind of major technologies you really want to look at. So the first one we're going to talk about is SLS, selective laser sintering. Basically, you're using a laser to melt powder. The powder bed, right, the build volume, is filled with powder, which means you can stack your parts in 3D, right? Kind of create a three-dimensional XYZ pattern. And so if you've got a whole bunch of little parts and you need to make, 50 or 100 of something, you can knock that out in no time flat with SLS, right? And the next day, you could have the entire print bed completely full of parts with all these finished parts that are basically ready to go with almost zero post-processing. Great for low volume production, but it also does really good with fixtures and things like that. And the accuracy is great, plus or minus 0.3%. You probably don't want to try to claim anything more than about plus or minus 12 thousandths. And as the part gets longer, that adapts, but it's a very stable process. Stereolithography is even more accurate. It's got a much higher surface finish. That laser does a fantastic job of curing exactly where it needs to be with that laser accuracy. Depending on the material type, it's going to affect your accuracy. So for example, something that's a really soft material versus rigid, something, thin walls versus thick, those all have different considerations, but you're talking plus or minus 0.2% on the accuracy there. But then we start talking about FDM, fused deposition modeling. And I put an asterisk on this one, and it's doing a lot of heavy lifting because FDM is kind of frowned upon for its accuracy in most cases. So FDM, you might say, well, it's 20 thousandths, right? That's a pretty good idea. But the picture that I have here, that is of a Markforged industrial printer performing in-process inspection with a laser micrometer. Let's talk about what that looks like, because they're taking FDM to places no other company is. Nobody's doing this. So Markforged industrial printers, or they've got desktop printers, they got metal printers, but specifically the industrial series printers come equipped with laser micrometers. Those are used for machine calibration. So if there's any wear or any, damage or anything, anything's out of square or something like that on the machine, it'll actually calibrate itself and reverse that wear so that the final part is sort of, eliminated any machine considerations. It's also used for in-process inspection. So you can check to see that the part actually worked correctly and stop it and notify you if there's a problem. So you can take a look at it. And that part inspection feeds back into the slicer, which is powered by artificial intelligence. Now, this has been this way for many years. This isn't just like a brand new thing with the AI kind of revolution. The AI-powered slicing takes every part that's ever been printed, right? And it uses that to train the algorithm. Anytime there's feedback, it's constantly using that as data points and learning. The material we use is onyx. There's a nylon 6 material that doesn't have chopped carbon fiber in it, but if you put chopped carbon fiber in, that's what we call onyx, and it's extremely dimensionally stable. That's why it was actually developed. Markforged started using it. You'll see it now that most people have something similar to this, but Markforged was really among the first by a number of years building with this very stable sort of fiber-filled material. And then if you want even more stiffness, rigidity, dimensional accuracy, you could put fiber reinforcement in there. Now, we're not going to do most of that. We're just going to take advantage of the basics, and we're going to go and build a part. And this is my kids and my tractor, and specifically, we're going to be building this part here on the front of this tractor. So this is a grapple. It's used to pick up brush and logs and things like that. It's got jaws that open and close. And that actuator right there, it broke on mine, right? It's a 12-volt actuator, uses an Acme's thread inside with a motor. And when I opened it up and looked at it, they told me it was not serviceable, so I just ripped the thing apart and kind of figured out what happened. There's a plastic nut, Acme nut in there, and it stripped all those threads out. So I'm not okay overpaying for something that's going to break and is completely unserviceable. I'm going to bring my own to market, right? I'm going to start with a similar design, and I'm going to try to build as quickly as I can and iterate as quickly as I can any parts to replace and get out back in service. So challenge number 1, this is kind of our challenge for the day. I want to build a functional prototype of this part by tomorrow. That's a really fast turnaround, but that really underscores that time to first part. I want a part that's fully functional and ready tomorrow. And by that, I mean it's strong enough, it's the correct accuracy, it's all these things. And there's 3 major problems with the request of a functional prototype. Right? Everyone can make something that looks pretty, right? A little pretty boat, a little benchmark boat. But this one has extremely tight critical tolerances. It has a press fit dowel that needs to be press fit in. That's going to have an extremely tight tolerance and a very specific type of fit requirement. And it also has some very fine thread holes that need to be structural. So let's do this. Let's go build this part. And so I'm going to jump into SolidWorks. And here is the assembly that this goes into. And so if I grab this actuator, you can see here's how it goes in and out. This is not hydraulic. This is mechanical. There is an Acme screw in here that spins. This Acme screw is driven by a gearbox down here. So this gear has a clutch on it to keep it from stripping out this part, which, of course, if something lands on it, it strips it out anyways. So that's going to this gear stack and then to the motor. This gear stack is on this dowel pin, and the dowel pin is a press fit. So we want it to be a very specific type of fit. So that it fits correctly, it holds accurately and evenly, and it doesn't split the material. So the center to center spacing between these two bores, between the motor and this shaft and even that pin, those are all really critical. So we got a lot of work kind of cut out for us. So this is the part we want. This part is going to eventually be die cast, but we're trying to make something that will be functional long enough for us to do sort of our prototype testing. So Onyx is going to do a great job for us. So remember the three concerns we had. The first one was this hole-to-hole spacing. Markforged industrial printers claim an accuracy of at least plus or minus 0.2%. That's the same as the stereolithography, but it actually can go as low as 0.1%. So if you look at basically 3 inches plus or minus 0.2%, that's 6 thousandths. So we can't hit plus or minus 2, but we can hit plus or minus 6. Now, is that going to work for us? Probably, right? In prototype land, if you're off by a couple thousandths, you can shim it, you can kind of jiggle it, right? But in production land, that's not acceptable. I need everything to always be right every time. So this is going to suffice for what we're trying to do, but it's not perfect. The other tolerance we want to look at is this tolerance that we have on these press fit dowel pins. So it's a 6 millimeter hole for a 6 millimeter dowel. Now the dowels are really accurate, right? They're ground dowels. And so normally if you were pressing metal into metal, you'd need a very tight tolerance to be able to accommodate that. Well, in this case, there's no way we're going to hit 10/10,000ths of an inch up and 4/10,000ths of an inch down. We just can't get there. But we can hit a fit that we need. So if you think about a fit, right? Think about it like a clearance fit where it's free to move, loose fit where it's like jiggly, friction fit where you stick it in and then you can turn it with a certain amount of friction, and that friction has kind of a range of values. And then you've got clear or interference fit where you're actually just pressing it in and it's clamping that thing down. You got a lot of range of behaviors, and this dimension was for metal. What do we need? What size of hole do we need for 3D printing? And furthermore, when you specify a tolerance, normally what you're doing is you're doing it either as an inspection tolerance or you're telling them what type of process to use. So +3 and -4/10,000ths, that's probably a reamed hole, and that's perfectly acceptable for a CNC machine. We can't do that with additive. You can't just sort of go in there and finely add material to that. You either have to overbuild, underbuild, or aim at something different. And so in order to do that, what I'll typically do is build something like a unit tester. So this is what a unit tester might look like. This is the one I actually printed for me, and it has every size of hole that I think might be the right size of hole for this part. I don't know exactly which one's going to give me the best result, but I know if I print all of them this is a tiny little part. If I print all of them and then I sit this on my desk and I just sit there and play with it, I can say, okay, well, this one's loose. This one is, free, but it doesn't wobble. This one is this one is that. And if I print this and leave it sitting on my desk, I can always refer back to it and say, okay, for this next one, let's go like 2 steps tighter, right? The friction wasn't quite where we wanted it, so let's go from here to here, right? I got a range of values. It's almost like a thread guide, but this is for press fit. And so I can print that and then very quickly grab it off the printer and go and figure out what size I like. And when you come with 3D printing, nominal size is what matters, right? You can make asymmetric tolerances and a CNC machinist will just figure out how to hit the middle of that tolerance range. But with 3D printing, it's all about that nominal dimension. So here's what I'm going to do. I'm actually going to create a new configuration, call it 3D printed. And this 3D printed configuration is specifically going to have a different nominal dimension than the rest. That nominal dimension, I'm going to say show custom sizing. So instead of it being 6.0, I'm going to say it is 5.85 millimeters. That's the hole on my desk, on my unit tester, that fits exactly the way I want it with the right, stiffness from bending, and all that kind of good stuff. I don't necessarily have a tolerance on that, right? I know what my machine is capable of, but I also know that if I just tell it 5.85 nominal, I'm gonna get what I want. So it's kind of weird. You don't actually end up using tolerances with 3D printed parts. You may for inspection acceptance criteria, but you're not actually going to be able to do it to say, adjust your parameters to hit this size. It's just going to print what size it is. You're responsible for the nominal dimensions. I'm going to say this configuration only because I don't want this 5.85 dimension for all configurations. I just wanted to hear. I even turned off the tolerance so that it's very clear that in this configuration, that's the dimension we want. That's the nominal dimension we want, and we expect the final fit to be achieved. We don't actually know what dimension that's going to key out to be, but we know it's going to be a very repeatable dimension as long as it's printed in the same orientation. So we've got center to center spacing tolerance here that's going to be close enough. We've got a fit here that we can't hit the tolerance, but we know we're going to achieve the end result fit we need. And then the third one is those fine thread tapped holes. And so fine thread tapped holes, typically what we'll do instead of that is we will come in here and embed hardware. So I've created some hexagonal void cuts here. So they're inside. You can't see them from the outside. And what we're going to do is those are the exact size of M5 jam nuts. And we're going to print, and then when it gets to that top of that layer where it's got, the perfect shape void in there, we're actually going to insert hardware into the parts, print around them and encapsulate them, creating fully functional, full strength threads in effectively a plastic part. So let's do that. Let's see what that looks like. Let's get it over to the slicer. To do that, we got to save it as an STL file. So I'm going to do save as, and I'm going to say that I want to save this as an STL file. And we're going to call this Tolerances Webinar. And before you hit save, you really want to make sure to go into your options for STL files. Because STL files can be saved in different types of resolutions, right? CAD geometry is analytical. Circles are actual circles, flat faces are actually flat, but an STL is a series of flat triangles that approximates your curved part. And so what we recommend is you set deviation. So if you want like a really coarse part, that'll create almost that tessellated effect where it's looks like triangles. It's kind of a cool effect, not what we're going for here. I could do fine, but that's kind of arbitrary. And so what I'm going to do instead is I'm going to say custom, and I'm going to give it a tolerance of about 4 thousandths of deviation in linear, and then about 1 degree deviation in angular. And that's going to give me a part here of a certain size, and that's what I'm hoping for. Now you can clean that up or change that in any way you want. If you think that you want it to be more accurate or less accurate, just keep it under about 20 megabytes. That tends to be the sweet spot for performance. But this is going to give us a great job, and it's only about 3 megs, so we're doing really good here. So I'll click yes, and it's time now to go and slice it. So we're going to slice in Eiger. Eiger is the online slicing software, so you don't have to install anything on your computer. All you have to do is just log in and upload. If you're in a secure environment, you can use an offline version, but all we've got to do is say import STL, and then we'll go grab the file that we want. And we can bring in multiple ones, give them a name. This is our Tolerances Webinar part. We're going to do it as an industrial printer or part made out of onyx, and we're going to add it to my personal folder. So we'll import that STL and see how it looks. Now, a couple things here. The guys always tell me to set the units correctly. I never do. So I have to go in and say, this is metric or imperial to be able to get it the right size. So if it ever comes in just super off on your size, get in the habit of saving out the correct units or update that. But for this part, I don't want any carbon fiber because I want to go as quickly as I can. The onyx should be strong enough. We'll use the rest of the defaults and we'll go ahead and hit save. So what we're going to do and what we're going to get is a fully sliced model that's going to figure out where all the slices go, how the print head needs to move in order to achieve that and build up that layer by layer. And it's going to give us an estimate of how much material it's going to take, how much time it's going to take to print. Lots of really great helpful information, and we can kind of make some decisions. So this part's going to take about 14 hours and cost a little under $20. So not too bad. Now, if I was to, let's say, flip it over, right? If I flip it over, I can check and see, is that less expensive or more expensive? It is going to change which direction is up. It's going to change kind of the surface finish results we might get. So definitely kind of play around with the part. I may want to do it on its side, but for this part, because of these round holes, I want to keep those in the XY plane. This is going to be definitely the orientation, either this one or the original one that it came in. And if we look at it a little bit, we do have these hex voids that we're going to have to deal with that may be easier the other way around. Looks like the other way was a little bit cheaper. I'm going to go ahead and use that one. And then we're going to go ahead and go into the X-ray for this part because I want to show you what we're going to do to deal with those embedded pieces of hardware. Because the embedded pieces of hardware, it's going to print, and we need it to stop when it gets to the top of that void, that hexagonal void, so that we can drop that hardware in there. And so we have to establish that. Also, because that void has a top and a bottom, kind of a ceiling, a floor and a ceiling, there is going to be supports automatically calculated for those. We need to turn that all off. So here's the shape that we get, or the plan that we get, basically. And everywhere you see purple, that's where the supports are. And you see there's supports in these hexagonal areas. This other support, it'll come off pretty easily once we're done. But let's go into the 2D mode and let's just kind of look at each layer individually. And as we scan through the layers, you can see how it's going to approach things. It's a really nice way to look at like really small detailed parts to see, where the supports are or where the various different lines are going. But my main concern is these hexagonal openings right here. This layer is the very top layer that's open. I want to pause after this layer, so I'm going to create an override and say insert a pause. I'm also going to come in here and find the bottom of these voids, which should be right about there. That's the very first layer where this opening exists, right? The one right below it is the floor. So right there, that's where it's going to start building up supports to hold the ceiling. Well, there's not going to be a ceiling when we're done. So I'm going to go ahead and tell it to remove supports. And I'm going to have it add a sketch. And we're just going to sketch in these little areas right here. This one, and this one, and this one. These are the areas where we don't need any supports. So I'll say finish my sketch. And then I'm going to pull that up to about there, which should be the full height of those voids. And we'll check and see what that does. The slicing is all being done on the cloud, so it does a pretty good job of going very quickly. Even if you're doing it on your phone or a Chromebook or something like that, it doesn't really matter. So once it goes through and slices, it's going to give us a new estimate, and it's going to give us the new plan. And we're hopefully we'll see that there are no more supports in those hexagonal areas. And we're going to get a nice print feature or pause feature right away, or right at the top of those. So that's looking good. The material costs are $18.63 still, so not really anything there. So the part is now sliced. We don't really have anything else we can do in terms of accuracy, but there are things we can do in terms of strength. Now, Bryce Babinick did a webinar on simulation recently where he showed how to take and apply a very specific load case to a part to see whether or not it's going to be strong enough. But I don't have a specific load case. Right? I got some idea of how it's all going to be loaded up, but it's going to be stacked in with a bunch of other parts. I don't actually care about a very specific load, but I do want it to be stiff. So this is where I'm going to make a change to our account. So in the account settings, you actually have the ability to hide something called the Performance Advisor. And a lot of times companies will hide that kind of while they're working, because that Performance Advisor pops up here, and you can see it's generating print advice. That pops up and it runs a stiffness analysis. So for those of you that are familiar with FEA, this is running just a linear frequency analysis, trying to figure out the fundamental frequencies of this part, and then it's making, what if scenarios and creating advice for ways that it could potentially improve the strength by just changing a few of your settings. So I sped this up just a little bit so you could see, but the settings that it recommends are to improve the strength by 81% while increasing print time by 5 hours and cost by about $5. So what I can do is see what those settings are. And so what I'm going to do is hit Apply Settings, and you'll see that it took my wall layers from 2 to 8. That's going to give us this additional strength. So I'm going to go ahead and hit Save on that. We're going to reslice it and find out exactly how long it's going to take for this new design variation. All right, so we're still at 20 hours, so this is going to be done definitely by tomorrow. But the last thing I want to do before I go ahead and hit Submit for Review or Print, depending on how my systems are set up, I'm in R&D, so I'm just going to hit Print because who cares. But I'm going to turn on some scan settings. And with scan settings, what this allows you to do is scan intermediate layers to be able to see what the tolerances are. And the reason we're doing this is I don't want to have to put this part on a CMM to validate that this is an accurate representation of the design that I want to use in full production. If this fits and it's the right size, then I know that my design is good. If it fits but it's the wrong size, it doesn't do me a whole lot of good. I mean, I can continue testing, but I've got to go fix that for production. So I'm trying to create not just a functional prototype, I'm trying to learn whether or not my design is going to be suitable. So I would turn on this X-ray inspection if I wanted to. I'm not going to turn it on for this particular one because I've already printed one and we ran through and got the finished results. So let me show you what that looks like. On my builds, I want to show you the very first part we ever made for this design. And so that is this guy right here. The rest of them, we flipped them over so that we could print them the other way because the surface finish looked great on the bottom here, but this is not exposed. And so it ended up kind of giving us a really nice finish interior and not exterior. So we flipped it for the rest, but this is the very first one off the build. We printed this back in March. And what I can do is actually take a look at the build time, the material cost, but I can click on this part and actually start inspecting it as if I was using a CMM. So remember this hole right here, I can come in and click on it and find out what my surface area is, how much data I scanned off of it, what's my radius, right? Nominal versus design, where's the center, where's the axis direction, where's the angular deviation of that part. 4.8 degrees, that's probably about reasonable as far as the angular deviation. Luckily, this has a mating part on the other side that's going to hold on to it, so that deviation is going to kind of get pulled out of it, so it shouldn't be a problem. Let's take a look at our spacing, our hole-to-hole spacing. So I'm going to say from this surface right here to this surface right here, I want to know what the distance is. The center to center distance is 74.49. when it's supposed to be 74.51. So we're 0.02 millimeters off in terms of our center to center distance. We can take a look at the center line angle and everything else, but what we end up with, remember we said we wanted plus or minus 2, we expected plus or minus 6 thousandths, we're actually getting plus or minus 5 thousandths. Actually minus 5 is what we're getting in terms of that center distance. So we're able to very quickly grab that information. And finally, the really tight tolerance part here, this is the +1 - 0. For this one, it says mean nominal deviation is minus 0.04 millimeter, and it's at 18.51 millimeter versus an 18.5 nominal. 0.01 millimeters is the amount of deviation and variation we have. And so I'm feeling really great about this part. If this part functions correctly, we're going to be able to use this really effectively to do our testing and to validate that our design is suitable. Now, one of the things I did want to check was kind of the general trend of accuracy. And so we did print several of these for the various different events. And if you take a look, they do vary up and down, but generally stay within that range. The offset and the correction that the AI slicer does is not immediate. It's not like you print one and it's 5 thou over, and so the next one is 5 thou under, right? It's going to sort of try to dial that in over time, but the more times you print a part of a certain shape, the more it's going to try to dial that in and give you more and more accuracy, and that accuracy will improve over time, which is kind of a crazy thing to think, that your part is always going to be more accurate over time than when you first started printing with it. So here's a little bit more of that footage of it actually printing so that you can kind of see what that looks like. And so here is the finished part. This is part number 1. Part number 1 has those 8 wall layers that were recommended by the performance advisor. And if you try to break this, I can't even see it moving, and there's no fiber in this. This is just the onyx material. That extra wall layer, those extra $5 were absolutely perfect for this part. It's kind of hard to see, but there's some threads in here from those jam nuts. So they sat inside this really thin part, and they gave me a very structural hold on this. The spacing is good. That tight tolerance for the bearing, it actually fits and holds beautifully. Same with the press fit dowel. Everything's exactly the way I want it. So it really, I don't think anyone is diving to the depths and the complexity of controlling their processes, of controlling their slicing, of controlling their materials and everything else to achieve this level of accuracy, right? Every system, every manufacturer continues to push the envelope. Formlabs released the Form 4 recently, which prints extremely fast, accurate, and large parts. The industrial series from Markforged, they recently released the FX10, which is an awesome jump forward in terms of print speed, accuracy, and everything else, but it's building on that industrial platform. So if you have a situation where you've got a part with really specific needs, such as structural threads, strength, geometric requirements, take a look at this industrial printing capability from Markforged or from Formlabs. We can do a benchmark test and see if that's a good fit for you and understand what the very first part we print off for you can do for you. All right, I hope you enjoyed that. Let's go ahead and take some questions. If you are in the webinar, we'll answer those live to a full Q&A. For those of you on YouTube watching this in the replay, type your questions down in the comments, like and subscribe, all that kind of fun stuff. But I'll turn it over to our host.